Hello, my name is Mariana Frangides, and I'll be talking about topic number 24 of kinetics. So mostly we're going to be comparing first and second order rate reactions between each other. And the first thing I want to talk about is integrated rate laws, that are mathematical expressions that show how the concentration of a reactant or product changes over time during a chemical reaction. So what is going to change? They come from differential rate laws, which have previously been studied. With the addition of time, differential rate laws describe the immediate speed of the reaction, and integrated rate laws predict concentration at any point in the future or past. So we're going to be talking about that more in depth. And knowing the speed, the amount of reactant can be found after the reaction. And here we go, we're going to talk about first, and second. So for zero order reactions, the rate is not affected by the reactant's concentration, and the rate is constant no matter how much the reactant is present. So this is an example. This is the equation, and so we have A stands for the concentration against time, and K stands for the rate constant. AO stands for the initial concentration. So here's an example. I wrote it down. So this is from, I'm pretty sure, the homework problem, so I just wanted to incorporate it here. The decomposition of compound AB, so we're going to focus on that, and the rate constant is this, and we're solving the time in minutes for concentration decrease, 26% of initial concentration. So we have the equation right here. We're going to plug in the numbers. 26 is the concentration times time, and we have the rate constant, and then we have 100. And so the 100 isn't given to us, but we're just going to plug that in because we're just going to have a constant value. And then we solve for t because we're looking for the time, and we get this number, but it's in seconds. So we have to simplify that into minutes. So that's what we did, and that's how we found it. And just like I said in the beginning about differential rate, this would be a differential rate because we're solving for the time. And now we have the first order reaction. And so with the first order reaction, the rate depends directly on the concentration of a single reactant. If the concentration is doubled, the reaction rate doubles. So we can see a difference between this one and the zero, that it looks like there's an inverse sign for the beginning of the concentrations. So that is one difference. And then another difference is the first order reactions are half-life, and this means that the time takes for the concentration to half is constant and independent from the initial concentration. So we do have the equation here if we needed to figure that out. And then here's an example. Rate constant of, so I'm just wrote down the keywords, and the initial concentration of 1. So it wants us to calculate the concentration of reactant after 100 seconds. So this time we're solving for the concentration, so I did write down that we're solving for the integrated rate law because we are solving for the concentration. And again, we first have the equation, which is wrote down, and then I plugged in all the answers. I plugged in all the given numbers. So we have the 0.005, and so that is the rate constant. We have the seconds, and we have the initial concentration. So when working with inverse, we have to use the E, so that's what I used. And then we got the final concentration of 0.607 molarity. And so we found the concentration, and so that's that. And now we have the second order reaction. So in a second order reaction, the rate depends on the square of the concentration of one reactant or on the product of the concentrations of two reactant. If the concentration of the reactant in second order reaction is doubled, the rate will increase by a factor of 4. So in this one, now we see, instead of multiplying or anything, it looks like we're dividing by 1. So 1 over the concentration against T, and the same thing for the initial concentration. So that is a difference, and it is inverted. The slope will be positive, and K will be equal to K. Yeah, and the K will be positive this time. So that's another difference. So instead of the K being negative like the other, like the 0 and first, it will be positive because it is inverted, and so I just wrote down that little note, but I did a example. So this is what it would look like. I'm pretty sure this is from the homework as well. And so we have 1 over AB versus time. It's a straight line. And only for the second order, we notice that the slope is equal to the k. So that's not like the other reactions. It's only the second order, so it's important to write that down. And so we want to solve for the concentration after 90 seconds. So again, we're solving for the concentration, which is why I wrote down integrated rate law. And so I would have the equation right here. I plugged in all the numbers. Again, the rate law is the slope, so we wrote that down. We have 90 seconds. And then the AB concentration, or initial concentration, is 1.150, so I wrote that down as well. I plugged in all that, and so we got the concentration, the first concentration that we're getting, but that's not the final answer, because we still need to plug it in like we did with solving for concentrations in the other chapter. We still need to solve this. So we do have the initial concentration here, we have the change, and we know that that will be the final concentration. So we need to figure out the x though. So that's what we're solving for. So we plug in 0.150 minus x equals this number, because that's the concentration that we solve for. And then when we solve for x, we get 0.137 molarity, which is the concentration after 90 seconds. So we did that, and we solved for that, and that's it.